to these databases, and it's the most powerful way to express complex queries over tables. So even if we write code in Python or Java under the hood, a lot of our applications still depends on SQL. Of course, you are all more senior than me and still remember Stack Overflow website. In their 2024 survey, SQL is still the second most used technology among professional developers. But why we need text to SQL? Every team in a company which lives on data all wants answers now. Instead of filling a ticket for the data team, they just ask a language agent in plain English. The agent reads the question and chooses the right warehouse and SaaS tools, and then has to generate code to get the answer. Which in our case, that code is SQL. So basically, here we are dealing with the code generation problem. Um, this slide shows what text-to-SQL actually is. A user asks a question in natural language, for example, which five leagues have the most matches? We also give the LLM the database schema for this football database, which has tables like country, league, match, and their columns. Um, then the LLM uses the question plus the schema to generate the SQL query. After that, we run that SQL on a database and get the results table which answers the user questions. Now let's see what is happening under the hood. Modern text-to-SQL systems usually follow three stages: retrieval, generation, and correction. I quickly walk through each one. First stage is retrieval. The system takes the natural language query and then full database schema. It selects relevant tables and columns using a schema linker component and a few relevant example for few shot prompting and some hints from documentations. The goal is to show the LLM just enough context to solve the task without overwhelming it with the entire schema. The next stage is generation. Now the LLM gets the user question plus the retrieved context and generates one or more skill candidates. Many systems add custom methods here. They might decompose the question and predict key SQL pieces or sample multiple candidates to increase the chance that at least one of these queries is correct. And the final stage is correction. It runs the candidate SQL queries and checks for errors or weird looking results. Based on the feedback, the system tries to fix a query and can regenerate it up to, for example, n times until either works or we hit the limit. Now let's look at how people evaluate these systems today. Most works uses public cross-domain benchmarks like Spider, Bird, and Newly Beaver. Um, like the typical ML problem, all the data is split into train, dev, and the hidden test set. Test is actually not available to anyone, so that no one cannot cheat on the benchmark leaderboard. Each benchmark data point has a natural language question plus optional hint, as you see in this JSON item, a ground truth SQL query or gold query, and the underlying database files and schemas. Also, they typically use execution accuracy or EX as the main metric, which I explain later. Now I'll focus on two main problems this thesis looks at. First one is pipeline cost. Here's why that's an issue. For example, we have a simple question like name of any sports organization. That's basically a single table lookup, returning one row or a small list. Also, we might have a complex question like identify our five sports organizations with the best and worst quarter on quarter financial performance in Canada for Q1 2024. You can see the SQL of these turns into multiple CTEs, joins, aggregations, and calculations. In most systems deployments, these two get treated the same way and use the same big expensive model. That means many simple exploratory questions become unnecessarily costly and slow. This is what motivates us to propose the first LLM router in text-to-SQL systems. This work is published at NeurIPS 2024 table representation learning workshop. The second thing that exists right now is that as a developer of these systems, evaluation is challenging. The first part of this evaluation problem is metric. Almost everyone uses execution accuracy or EX. It's binary. If the predicted result table exactly match the ground truth table, you get one. Let me make a tiny example. The question is show total revenue per customers in 2023, and the predicted SQL query produces exactly the same table as the gold query at the bottom. So in this case, EX is 1. That's perfect. But if new predicted SQL query add an extra column like country, it is still clearly answers the questions. You could just ignore that column. However, EX here immediately flips to 0, and that's wrong. Or if instead the predicted SQL query keeps the same columns but adds a filter like year more than equal and greater than 2023, we got some extra rows for other years. Again, the original answer is still sitting inside the table, but the EX is 0 once more. So with EX, a query can be almost right, maybe one small edit away from the correct version, but the metric still just says 0, and that's terrible signal for both training and debugging purpose. The second challenge in the evaluation is data itself. In benchmarks, table and column names are usually clean and descriptive. Here, like student and measure. But in real enterprise databases, names are often heavily abbreviated or cryptic, like ENR underline DT, which means enrollment date. That kind of naming makes the mapping from natural language to a schema much harder, but current benchmarks almost never reflect it. So text-to-SQL developers get models that looks good on nice and clean benchmarks, but they are not really stress tested against these enterprise style data. That's why we built SQLmorph, an open source evaluation framework with fine-grained execution metrics and query mutation methods for stress testing. This work is almost accepted at ICDE 2026. Actually, we got 3 week accept and we just submitted the revision. So it hopefully get accepted next month. Now I'll move to our contributions, starting with how we make SQL generation more efficient. Our solution to the first problem, pipeline cost, is to add an LLM router that chooses the cheapest capable model per query. To study this, we built our own text-to-SQL systems called VirtuSQL, which we use as a test bed for our experiments. It follows the same 3 stage pipeline I showed before. The nice thing is that each stage supports different techniques. I'll skip the techniques in pipeline due to the time constraints. Now that we have the pipeline in place with VirtuSQL, I want to zoom in on just one decision inside it. Which LLM do we use to generate the SQL? Instead of always calling the same big expensive model, we add this idea of routing to the generation stage. For each incoming query, we want to pick the cheapest model that's still good enough to get the SQL right. Formally, you can think of it like this. For given n models, M0, M1 to Mn, an NL query queue, identify the weakest model MI that can accurately generate corresponding SQL for queue. The first router is pretty simple and entirely based on history. When I say historical data, I mean for each old question or basically train set, we already ran all the models and we know exactly which ones got the SQL right. So when a new NL query or natural language query comes in, we embed it, look into that log and pull out the top K most similar past questions. That's our leader neighborhood around that given question. For each model, we then ask on these K neighbors, how often did this model get EX equal 1? That fraction is the model's scores for this query. We compare that score to the threshold alpha. If the model's score is below alpha, we say this model is probably not reliable here. If it's above alpha, it becomes a candidate. Among all the candidates, we pick the weakest and cheapest model whose score is at least alpha. If nobody passes the threshold, we treat the query as hard and just send it to the strongest model. Second router is classification based. It trains a small BERT model to directly say which model for each given query. We start from the same historical data for every past query. We know the question, the schema, and which models produce the correct SQL. From that, we built labels for each query. We mark the weakest model that was successful as the label 0, 1, 2, and if all models failed, we give it a non-label. So we have four labels. It's basically a classification task. Then we fine-tune a distilled BERT on this data. The input is just the natural language query plus the schema. The output is that target model label. At inference time, it's super simple. Now query comes in, we add the schema, run on BERT forward pass, and get a label and route that to the model. For the experiments, we use the BERT benchmark. It's cross-domain and has over 12,000 NL SQL pairs and almost 100 databases. Also, we report numbers with execution accuracy metric. And we also use a small embedding model from OpenAI plus GPT-4o, 4o mini, and the Llama 3.18 billion quantized version in our router. Here I'm comparing how our three base models behave on the same queries. You can see there's a big overlap in failure. So routing won't magically beat the strongest model on accuracy, but there are also lots of queries that the cheaper models already get right, and we don't really need the strongest model. So the hypothesis is if we can detect which queries are easy enough, for the smaller models, we can route those away from the big model and keep almost the same accuracy while we are cutting the latency and dollar cost. Here's what happened. We actually plug the routers into the systems. If we also if we always use GPT-4o, we get about 61% EX, and that's our best accuracy but most expensive baseline. If we always use for O mini, it's much cheaper, but accuracy drops to 49%. And with Llama, it's even cheaper, but accuracy goes down about 29. But our router sits in the middle. The best score-based router accuracy is around 60%, and the BERT router is around 55, while being up to 1.4 times cheaper than always using GPT-4o. So the takeaway here is we stay very close to GPT-4o's accuracy, but we don't have to pay GPT-4o prices for every single queries. With the score-based router, we can actually tune how the system behaves. If we increase the threshold, the router becomes picky. It trusts only models with very high path success. So more queries go to GPT-4o, and we have higher accuracy but higher cost. In practice, a product team can just pick the threshold that matches their preference, whether they care more about the accuracy or they care more about staying with budget, even if developers sometimes has to iterate on a generated SQL that might be wrong. On this slide, you can see extra time the router adds to the pipeline. The score-based router adds roughly half a second average, and the BERT 1 second. Actually, the overhead is pretty small compared to overall text-to-SQL pipeline. The second challenge of thesis is evaluation, but I have to skip it. But in summary, we try to add a notion of precision and recall to evaluation part. We introduce new metrics, EXP, EXR, and F1. I'll skip the explanation. And basically, we don't have any more binary metric. We have a spectrum from 0, 1, and we can evaluate and debug the systems better. Also, on query mutation sides, we introduced TQA. And as you know, text-to-SQL data has two parts, text and SQL. On the text side, we try to augment the data with less natural form, like this. As you see, we augmented the data. And we also introduced another query mutation on SQL side, which called JQE. We basically think of database schema as a graph. Tables are nodes and joinable columns are edges. So we try to add more nodes in between and make the query harder, and this leads systems to fail. Let's wrap up things. We built SQL and added an LLM router so we can route each query to the cheapest LLM that can still generate the right SQL instead of always using the biggest model. On evaluation, we move past binary EX with EXP, EXR, or execution precision, execution recall, and F1. We see how a query is wrong, not just that it failed and it's not binary anymore. And TQA and JQA is a fixed benchmark into a family of harder but still control variants. Thanks, everybody.
All right. Thank you so much, Mohammed Hossein, and congratulations on your successful thesis defense.
Thank you.
Excellent research. Does anyone have any questions for Mo? Oh, I see lots of clapping.
Thank you so much.
Anyone has any questions, please feel free to take yourself off mute.
Hello, can I have a question?
Sure, sure.
Yeah, thank you for the great talk. I want to ask a question about correction step in your pipeline. Like in the pipeline, in that step, you need to get the feedback and then send back to the model, right?
Yeah.
I wonder how can you verify the query without using ground truth?
Exactly. Basically, for example, in our simple pipeline Word to SQL, the SQL corrector checks whether that query is parsable and runs on a database or not. It has, for example, syntax error or those kind of error, or is there any incompatible things in the query? For example, query has a random column which not exist in the real database. So we basically have execution based feedback. We run the query, and if we get error, we pass that error and the whole schema to the LLM again, and we ask LLM to generate a new query. So we basically don't use the ground truth query. We have execution based feedback.
Okay, I see. It's like compilation error, right?
Exactly, exactly.
I see.
Or
Thank you.
in some systems, in modern systems, for example, we pass multiple candidates to the correction pipeline, and based on some execution scores that those system implemented, they decide which query is more accurate, and it tries to improve the query.
Okay. It's like choose the best option.
Yeah, choose the best option. Also, correct any possible errors. Yeah.
Okay, I see.
Or we use LLM as judge to check this query seems okay or not. Yeah.
Okay, I see. Thank you.
You're welcome.
Thank you, Anne. Toyosi, please go ahead with your question.
Yeah, just a quick question,
Sure.
like a follow-up question that on the last asked one. I wanted to, since you mentioned something about it checks for execution if it works or not. Does it check situations whereby, for instance, you try to query a column that exists but it's not part of what's actually asked? I don't know if you understand what I mean.
Can you repeat your question? I didn't get it.
I mean, say you're trying to query what you're trying to get. Okay, so based on your answer on the previous question,
Yeah.
you said that it checks if the queries can be executed, right? Which means if you put a column that does not exist in that database, there will be an error.
Yeah.
Is that correct?
Yes.
So
Yeah.
I'm now asking that, what if the situation is that the columns exist, but they are not related to the question or the query that is needed to answer that question?
Mm, uh, Still, I didn't get your question exactly, but The correction phase basically try to parse the query with typical SQL parser or even run it against the database. If it got any kind of errors, for example, there is syntax error or I don't know, there is no such a column that exists in current generated query. LLM tries to fix that generated query. Basically, we don't want to make the EX one in a correction phase. We don't have the grand rules. We just try to improve the generated query.
Okay, all right, thank you.
Yeah, you're welcome.
Okay. Does anyone else have any questions for Mo before we proceed to the next speaker? No? Okay. All right. If that's the case, then thank you very much, Mo, for your presentation.
Thank you.
And we will now hear from Sylvain. Sylvain, please take yourself off mute and share your screen whenever you're ready. Okay, you're still muted.
Okay, thank you. I am Sylvain from Polytechnique Montreal, and I am going to present you a paper that has been published in 2024. I was supervised by Prof. Foutse during this work and other of his PhD student that has already graduated, Agvan Moradi, and forgot the name. Thank you. So the name of our work is Chain of Targeted Verification Question to improve the reliability of code generated by LLMs. Okay, let's first start by looking at the phenomenon. Let's observe that we can observe hallucinations in what LLMs can generate. This is an example that was took in the paper Chain of Verification Reduces Hallucination in Large Language Models that was published. The example was name some politicians who were born in New York, and then we got like some answers. And then in those answers, we observed that for some cases it was false. And then they proposed in that paper that they could now get from the answers from the LLM and then generate corresponding questions related to the answer. Like in the step 2, you can see here where was Hillary Clinton born, where was Donald Trump born, and where was Michael Bloomberg born. And then we got the answers, and then they get now the final answer. And then with the final answer, we got a real or a better answer. So since we are observing, we can observe hallucinations in code generation. We want to see in this study if we can map the same process to reduce hallucination in the code generated by LLMs. That could help us now to reduce the loop of executing the code through the unit test, getting like grazing of some errors, sending back to the LLM, doing that loop till we get a code that can be compiled or that won't generate some hallucinations, that do not contain hallucinations. So this is an example of a generated code by an LLM that contains some hallucinations. Here we have the function call get element text that is not defined anywhere. We have the variable much we did. Okay. Yes, so yes. Okay. So we have the function call here that is not defined, but it's used in the in the code. So the question now is, how can we, when we have the first version of the code, how can we update the code without executing it and reducing the raising of hallucinations? So we have three major research questions that are interesting us in this research is how to mitigate hallucination or other kinds of error before the execution of the code. Here is because we don't want to be doing the general process that we were used to do, executing the code, sending back the code with the error traces, and then getting the answer from the LLM, and maybe other errors are still present or other hallucinations are still present in the code, and then doing that loop n times. And then the next one is, do we want to know if rephrasing our prompt can impact the performances of what we propose? And then the next one is, how do our process impact the correct version of the code? So here we want to know when a correct code is generated, when applying our process, do it impact positively or negatively the process? So we want to measure it. So what is the approach of our work? The first thing is to collect the generated code. We will take the example that was, we will use the example that was presented at the beginning, the same function. This is it. We will now extract the AST node, the abstract syntax tree nodes of the function or the code generated by the LLM. We will extract different type of nodes. Here we will focus on two type of nodes, the function calls and the attribute calls. The attribute calls here is like if you have an object that is calling something like with pip date stripped. This is one case of, oh, sorry. This is one case of generated, this is one case of attribute node. And then we have the function call node that is get element text. So we can apply this process for different kind or different type of nodes. So we extract these different nodes that can be root causes of hallucinations. Then the next step now is to send to the LLM a prompt to ask him to verify that those nodes are not a source of hallucination. So we will define for each kind of nodes, a corresponding prompt, and then we will send it to the LLM, showing him now with a few shots the buggy code, the prompt, and then the correct version, so that the LLMs will just correct the code and then show us now the final version of the code that we are waiting for. So we have the few shot prompt, the verification target, which contains the wrong attribute, the hallucinated object, or any other type of node that we could define if we want to extend this study. But in the current study, we just focused on two types of errors, the one that was occurring through wrong attributes and hallucinated object. So this is the process. And then at the end, we have a repaired code. And then that repaired code, we go through a testing phase to evaluate what is the impact of our process. So now, what about the data set and the environment setup? We went through a data set that was labeled from the coder eval data set. We get the code that were generated by LLMs and labeled either wrong attribute or hallucinated object. So we filtered from that labeling all the codes that was having wrong attribute and hallucinated object. And then we get from them 61 buggy codes related to 31 tasks. And then we did like 5 run times. The LLM that was used for the process of correcting through targeted verification question was ChatGPT 3.5. And then the experimentations has been done on a Docker environment in a virtual machines. So relative now for the first question to know what is the impact of the process. So we observe that using the general verification question, that is the process that we are used to, like getting the answer from the LLM, asking to the LLM to verify that there is no error that will be raised from the generated code. We observe that our method reduce more attribute error than the general approach. It reduce better the occurring of name errors than the general approach. And then, but for other kind of errors that has not been presented in the prompt, you observe that our method does not really reduce the errors compared to general verification questions. Then what about the rephrasing? Relative to the rephrasing, we observe that the performances are not degrading when rephrasing our prompt. So our results are not really depending on the quality of are not really depending on different words or selected set of words. So the prompt does not really impact the performances of our approach. So we can say it with these histograms. So, and then at the end now, when asking ourselves to know what is the impact of our process on the correct generated code, we experiment it on 54 correct code corresponding to the initial task. And then from it, we got 2 test failings. We saw, let's say that here we executed this process 5 times. That's why we can see these mean measures. So from the correct code, we saw an insertion of 0.2 attribute error. So in one case, from correct code, we saw that the generated after executing our process on the correct code, we saw like a mean of 0.2 name errors and other errors 3.8, meaning that when sibling, like some notes, our process does not really insert many errors, meaning that when applying this with this approach, we have some assurance that the code that will come from it will not, or will, the probability to insert errors is very low, but we are sure that if there are hallucinations in the code, our approach will reduce those hallucinations. So what now can we remember from this study? Our method helps to get improvements compared to the baseline and helps to control the improvements on potential buggy nodes. Our method doesn't turn many codes into buggy ones, and we observe that rephrasing doesn't really affect the performances of our approach. Thank you.
Hey, thank you, Sylvain. Does anybody have any questions for Sylvain? Oops, I don't know if you have any comments about your 2 students. Anything you can share with the group about their experience as master's students under your supervision? I can see that they both put a lot of work and effort into their research, so congratulations to them. No questions for Sylvain, really? Everything's clear?
Yasmin has a question.
Okay, Jasmine, please go ahead.
Can you hear me?
Yes.
Yes.
Yes. Okay. Thank you, Sylvain, for this talk. I just had a quick question, maybe on the slide where you said that you used GPT 3.5. Is that
Yes.
correct?
Yes.
I wanted to know if maybe like it's a high level question, but if you think that there would be any sort of changes, because now we're like at GPT 5.2 or something like that, if you think there would be any sort of changes to the performance of your approach using maybe newer models, or if it's part of maybe future work for you.
Okay, so these questions comes well. Surely since the models are getting better and better, the I think that we still have hallucinations in the in some task when we want to execute some tasks. Last time I wanted to write a script, and then the LLM proposed me like some arguments of a command that does not exist. So I don't think that maybe in code generation task exactly, this approach won't be as performant with ChatGPT 3.5. Like today we have GPT-5, but since maybe in some cases we are using like less capable models that have least parameters sometimes in our computer with local models when trying to develop, and for more general purposes that are not only focusing on code generation to solve specific problems, maybe in other sectors, this way of thinking can be applied to reduce the hallucinations. So I just think that the threshold will just move from the previous performances to another sector, another type of task in software engineering, but
Yeah,
the
it's
way
kind
of
of
thinking remains
sorry.
the same.
I have a follow-up question on that. So maybe now your approach is you can apply it to maybe like more traditional workflows we have with code generation, like you send a request to write some code, you get the code. But do you observe such hallucinations, let's say in more like a agentic context where the model has access to the whole context of your project, for example? Like, could you apply your approach, or there's less hallucinations in those cases?
In our we didn't go in the cases with the cases where we were working. It You were just taking the data set of coder eval, and then in the data set of coder eval, in some cases you could have a context, and in others you will just have a like the beginning of a function like match date like this, the comment, and it was asked to write the rest of the function. So in the cases where we got hallucinations, sometimes you could have the context and sometimes you don't have the context. So it's not like if it was calling a function that could be defined in the project, but in the current file, it's not. It's just that sometimes you just see the model calls a function that doesn't really exist in the file that you use to prompt it. So I I don't really know if I can say that the updating the context could be I don't know, the best approach to remove hallucinations. I don't have elements to answer to it.
Oh, thank you.
All right. Thank you, Jasmine, for your questions. Last opportunity for anybody to ask any questions or make any comments about either Sylvain or Mo's presentations. No more questions. Okay. That's the case. We're going to wrap it up a little bit earlier than usual today.
Maybe I have a question. What next? A question for Silva. Like, how do you plan to build on this work? How do you see hallucination mitigations problem going forward?
Oh, there are studies that try to explain why hallucinations happens in generated output by LLMs that are more theoretical explanation that are due to the way the models are designed. So, but now relative to my study, how can we continue or how can we build on it? Maybe this kind of process can be integrated in like it can be a process that can be what do you say, a layer before producing the last version of any code. It's like it's a phase of re looking back by the LLM what has been generated to ensure that what the user will test will have the least possible errors, and then the least possible errors to reduce the I don't know how will I say, the deception of the user, or encourage the user to use LLMs to assist in the engineering. So this approach can be extended either in writing scripts that can be related to other tools, maybe deployment scripts, to ensure that the way the scripts are written do not contain some kind of errors that could be related to the quality of data on which the LLMs has been trained. So it can be a layer that can be added in any kind of process in software engineering. We just need to adapt it to what we want to design, or to which kind of error we want to reduce the occurrences.
Okay.
I think, Sylvain, that was an invitation to do your PhD. Continuing research. Am I right, Foutse?
Yeah, he's still in the program, so.
I know, he hasn't graduated yet. Okay. All right, so thank you very much, everybody, for joining the talk today on a Friday at just before lunchtime. Just a reminder that these talks are every month, and we have a lot of students, actually master's students, who are graduating this year. So we will be having these training talks monthly. February is a really busy month because we have an industry talk middle of February, and then we have our next training talk on February 23rd. So I'll be sharing details about both of these talks with everybody very soon. But for now, thank you again for joining, and have a wonderful weekend, everyone.
Thank you.
Thank you so
Bye-bye.
much.
Thank you.
Thank you.
Mhm.